So welcome back, everybody. And these are certainly some of the giants who have shoulders to be stood upon relative to super hot rock. So I want to go back and think and discuss for a few minutes on key innovations. But before I do that, I want to mention that we're going to have some internal discussion here, and then I'm going to follow that by selecting some of the audience questions. I've already got some of them in front of me. If you want to submit a question, put it in the question bar at the bottom of your screen. So I'm going to go back to this question of innovations. I'd like to talk a little bit about key innovations that we need to go forward. Okay, well, so I'll pick on Egbert. How about a few thoughts continuing on that? This is a challenging new form of geothermal. There are many innovations that will be needed, but is this too heavy a lift? Can we do it? What does this mean for geothermal in general if we're successful?
Well, I can say a few things about that. And as I mentioned before, I'm a geologist, so I'm looking more in the geological details. And I think what's really necessary is to better understand the meaning of the parameters we are measuring and transfer them to geothermal properties. And that might be a little bit different when we look deeper into such resources where higher temperatures and higher pressures are encountered. And for that reason, it's really essential to better understand what is the meaning of the information from this part of the reservoir. And that might also be different compared to conventional geothermal sites. And what can help us in that perspective, and now we focus a little bit more on the innovation part in this field, is to not only collect data and compare them manually, but also use techniques like machine learning techniques, for example, and other technologies to better understand the data which we don't see visually when looking at certain parameters. And I think this can help to better integrate different data sets. In the past, it's always it is still a challenge to work with geophysical data and geochemical data. And this is just one example. And I think here we need to bring those disciplines together and work with a more integrated approach. And this is one part of the innovation that's required. And I think also on the visualization, we can do much better. Not only work with maps and 3D models, but also with virtual reality, for example, that gives you a much better feeling of the reservoir and the properties you are interested in. And this is my feeling, and I've seen that from other examples, and it's quite helpful to work with those new technologies.
Any other comments?
Well, I can comment a little bit on the innovation. It is quite clear from our experience in Iceland, these two deep wells or magma wells drilling into 900-degree hot rock. We proved that we can do it because we did it 3 times and got away with it. And we can produce from this magma interface and create a magma EDS, enhanced geothermal system. So, but what was one of the problem was not the fluid itself, because when the fluid is at a supercritical or super hot condition, high pressure, high temperature, it is relatively inert to the casing material, except for possible hydrogen or sulfur embrittlement. So we need very high quality resistant casing material, which can be thermally cycled by heating and cooling, and also resistant to embrittlement or hydrogen entering through the steel and so forth. So this is what is absolutely critical to be dealt with. And we also need to have something, because we will be producing at superheated conditions or super hot conditions, say 400 or 500 degrees, but not necessarily a supercritical pressure. So we can be producing, say, at 150 bars instead of 350. So that is okay. Then we have to deal with it on the surface. And evidently we have to have surface equipment to deal with the fluid too, where we can treat the fluid to mitigate for some bad chemistry, like we have already done. So in my opinion, I think we do have the technique, we do have material which we need to test. We do have fields that we can test. And in my opinion, we just need funds to do some, say, 10 wells in one field and do it quickly, because if we want to have any impact on the global warming, say, with supercritical conditions, which is relatively carbon-free, for instance, the IDDP 1 well in Krabla had less CO2 than atmosphere. So we could have gained CO2 credit from that well, because the CO2 was left up in the reservoir. So we need to move fast if we want to make an impact. And so we need some funds. So where is Bill Gates and all those big shots who can have maybe put some 10, 15 wells in proper sites and do it in less than 10 years, say 10, 15 years. If we continue at the rate we are continuing at the moment, it will take a decade, several decades to complete our mission. And
you bring up a really interesting point there, Ómar, and that is, how do we do this fast enough to make a meaningful contribution to reducing greenhouse gas, and not to mention the energy security issues. If it were successful and you were able to drill deeply enough to access these resources in dry rock, and be able to generate, to create reservoirs, then we really have something that's transformational. I think that's kind of the Rosetta Stone we're talking about here. So let me go back to Geoffrey. So how in your mind does a hydrothermal system differ from a hot dry rock system? So if you have a hydrothermal system, what kinds of differences do you see? You touched on this before, because you had essentially a dry well, but it was located near or adjacent to a hydrothermal field. What are your thoughts on those differences and what we need to do to demonstrate successful demonstrations in hydrothermal systems, but then translate that over into hot dry rock, where we could really, essentially scale up?
Well, for sure, the difference between a natural hydrothermal system and a hot dry system is the permeability. Of course, we don't have permeability in hot dry rock system. So this is why we need to, let's say, create it, or at least generate it, like the experiments that were done in France, in Sulz. So the big difference is this between the two systems. In Ardorello, the scramble well reached the bottom of our hydrothermal system. So from where we have permeability, in which we have the steam circulating in the rocks, from where we do not have permeability, and in fact we did not find any fluid inside. So the big difference, and what we have to understand, and it is part of the innovation, as we were saying before, is how to generate a permeability sufficient and economically feasible in this hot dry rock system to spread those globally. I mean, one of the key points is to understand the global potentiality of this hot dry rock system. So where and how much we can spread those everywhere on the planet, or just in particular situation where we have hot at shallow shallow depth, of course. So I think this is also one of the questions where to demonstrate the feasibility of this type of systems and then spread those all around.
Mm-hmm. Nori, in Japan, isn't much of this funded by the oil and gas? Where's the, there are questions, a number of questions in the chat basically about funding and where could you get funding and how could you do this fast? And Ómar brought up, drill 10 wells, and sometimes we talk about drilling 100 wells and drilling fast and allowing yourself to fail and learn kind of the model of unconventional oil and gas. But what is the role, Nori, of the oil and gas industry, if any, in Japan in developing this new technology? Is NEDO the consortium, including the Japanese oil companies?
Yes. The Japanese oil company, they have some interest in the developing of supercritical geothermal reservoir, and also we have the two policies. One is the nuclear, and another one is the renewable energy. And now the Japanese government is pushing the both, yes, and also the petrol oil company, Japanese oil company, also they have a lot of interest to develop supercritical geothermal reservoir, geothermal energies, and permeability is a critical issue in terms of development of the supercritical geothermal reservoir. But our calculation, based on our numerical calculation, the minus 15 square meter is enough permeability for development of the supercritical geothermal reservoir. So in the conventional geothermal reservoir, the minus 12 and the 10 minus 12 or 10 minus 13 is a normal permeability. But in supercritical conditions, the viscosity is quite low. In that case, the minus 15 is commercial. It's possible to develop as a commercial base. So now the petroleum company, they are thinking about the development of supercritical geothermal reservoir, which is permeability is minus 15. That is our concept and strategy.
One interesting piece from your work in Tohoku University is public. When we talk about innovation, we probably have to innovate on the public side. We have to get better at going out and reaching out to the public, because we may at some point be going outside of places, brownfields, places that are used to geothermal development. And I think, Japan is probably the most difficult place to do this, it sounds like, because of all the hot springs and the national parks. Yeah. So what have you learned about that? I mean, to take a little bit of a different tact here, there is, a real issue with geothermal anywhere, and that is public acceptance.
Yeah. So we have a very big problem with onsen hot spring owner. But the supercritical geothermal reservoir is completely different from conventional geothermal reservoir. We are now thinking about double layers of the geothermal reservoir. One is a supercritical, and another one is the conventional geothermal reservoir. And here is a high temperature acidification zone, which is a cap log of a supercritical fluid. So double layers, the supercritical layer, and this is a high temperature acidification layer, and this is a conventional conventional geothermal field. It's the two different stages. That is our concept of a geological model of supercritical geothermal reservoir. So the onsen owner, hot spring owner, they don't like to develop conventional geothermal reservoir, but supercritical geothermal reservoir is very deep, about 4 kilometers. So in that case, it's not so big effect to hot spring on the surface. So that is our strategy instead of conventional geothermal reservoir.
interesting, a technical solution.
I can maybe add one thing about this hot dry rock, because hot dry rock is what are you talking about? Are you talking about 200 degrees in continental Europe, say, as hot dry rock, like in UK or Europe somewhere? And there's a huge difference between hot dry rock is at 600, 700, 800 degrees, and rocks at 200-300 degrees. So when you're drilling into such high hot rocks, like say 600-700 degrees, the thermal difference between cold drilling fluid and the rock is enormous and apparently sufficient to crack or thermally crack the rock open. So you create some micro cracks around the wellbore during drilling, and we were actually observing this in our second well, drilling between 3 and 5 kilometers. We were having a seismic zone. There were no micro earthquakes before drilling, but during drilling, there was a micro seismicity that was building up, absolutely related to the drilling itself. And the reason was that we were thermally cracking the hot rocks because the thermal difference was several hundred degrees. And I think that's the key issue, to have sufficient difference in temperature to crack it open. Evidently, people are afraid of seismicity. And the largest seismic quake that we saw related to the drilling was less than 2 in magnitude. So we are maybe just lucky to be on a divergent plate boundary, where plates are separating, whereas in Japan is going under, and that maybe create much larger quakes. So again, geology is a key factor and structure here. So there may be difference from one side to another, really.
Yeah, I agree. Yeah. Iceland, Japan is completely different tectonic setting. We are subduction zone. You are the mid-ocean ridge, so it's different. But yes, we have to learn.
And the fastest learning is by drilling. I tell you, let's go.
Drill, baby,
we can do
drill.
It. We can do
it. So if we had time, I'd take up like the question of how do we fund this? But it actually, there are some questions in the chat. I have a whole log pile of questions here that I can only begin to touch on.
Can I just quickly
go ahead
to the discussion we had, because I think this is something which is probably also interesting for the audience. There are different concepts how to actually exploit the reservoir, and this could be like a single well concept, and you're stimulating the existing hydrothermal reservoir above, or you think about multiple wells, multiple very deep wells, and also somehow enhancing the conventional geothermal system above that area. What is your experience with that? I mean, I've seen the IDDP concept. I've seen the conceptual model from JBBP, and I was just wondering if you could comment on that, what your concept is, or do you want to extract the steam from the supercritical well? What is the idea? What do you think is most likely a viable concept?
In Japan side, in the JBBP, we have two ideas. One is the mining of a supercritical fluid, and another one is it's a mining of heat fluid. Another idea is heat exchange. It's kind of hot dry rock idea. But we have still two ideas. One is the mining of supercritical fluid. Another one is heat exchange using the supercritical rock. We have still two ideas.
I think Guðmundur, you had this conceptual model, and
we were definitely in for both, because we were doing trying to create an ETS system as well, and observing that. And what we observed in the Reykjanes drill hole in southwest Iceland, drilling it down to 4 kilometers. First of all, the conventional system was permeable down to almost 4 kilometer depth instead of the bottom of the system, which was calculated to be or expected to be at 3 kilometers. And we also saw that when we were reaching down to this final depth, 4,650 meters, that we were having influence on the reservoir above. So to create an EDS system, very deep EDS system underlying a conventional system, we need definitely to have deep casings and then try to crack it open and then pump return fluids back into the, or brine fluid, shall we say, back into the deep reservoir to mine the heat and get pressure support from the overlying system. And I think that is very feasible way to utilize the hot resources. The efficiency I'm not quite sure about, but I would rather like to produce from the supercritical, as I said before, at least to try that, definitely, because I think the energy output is higher there. If you can do it.
We have 5 minutes left, and believe it or not, an hour and a half has gone that fast. We probably have 5 hours of questions here, and that makes me wonder whether or not you all be willing at some point to have a separate dialogue, maybe with some others, to continue this conversation, because a lot of important information, a lot of ideas, we're just starting to get going. You're starting to talk to each other about your conceptual models. So I would love it if we can talk about that, about how do we gather, how do we roadmap, how do we, what are the most important endeavors going forward. Certainly we've come up with drill a lot of wells, learn as you drill. But, one of the questions that I'll throw out really quickly was about laboratories. What is the role of laboratories in giving us some kind of an idea of what we're going to encounter when we're drilling into rock that we really haven't drilled into before? So I'm going to just ask you each to comment like 30 seconds on the role of labs. So I'll start with Egbert.
Yeah, it's very important. We also had this component in our project here at the GFZ, but also at the BGS in the UK. And there were some high temperature and high pressure experiments. And this is really important to calibrate the data measured from geophysical surveys at the surface and better understand what's going on down there. So we are working with that, and also for permeability tests, for example, and with different salinities of the fluids, and that's very important. Also later for stimulation.
Geoffrey, the role of labs to help you continue your deep subsurface work.
Yes, I agree with Egbert. I mean, they are really important because not only a lab for geophysics, but also to understand the behavior of the fluids in the deeper portion of the field, but also at surface, in order to predict any possible scaling of the fluid at surface and how it works with the surface equipment, of course. So I think that they have a big role in this challenging topic.
Nori, what is the role of the labs? How about rock mechanics, understanding mechanics of materials and seismicity?
Yes, in Japan, the seismicity is a very big social problem. So we have to reduce the induced seismicity during the development of geothermal energy. So the supercritical, high temperature, and the ductile regions, that is very important for Japanese society to predict the seismicity. So in this seismicity and also the scaling, it's a very big problem. So the supercritical conditions, the very low permeability, low dissolution rate is very low. So in the supercritical, it has some advantage for scaling. So that is our strategy, and also we are now thinking about the mining of rare earth element from the supercritical geothermal fluid. That is another benefit, another advantage of supercritical geothermal fluid, rare earth element as a precious element from the fluid. Not only energy, but also the resources.
Ómar, give you the last word here.
Okay, yeah,
The role of laboratory.
chemistry of the fluid is of a key importance here. And we don't know the chemistry of the supercritical fluid, except partly. And doing experiments on surface with the in control setting, we don't know the proper fluid chemistry that we are dealing with. So that can change, and thermodynamic properties of supercritical fluid are non-existent. So this creates difficulty in doing lab experiments that are meaningful compared to doing the experiment in nature by drilling deep and test it. But it will probably be some sacrifice, like we already have experienced. We will sacrifice few wells on the
Okay, so thank you, everybody. This has been a great, a really great a dialogue. I'm going to pass along some of the questions to my colleague Philip for the next round. Some of them are germane to new projects as well. Thank you all, and much appreciated. Nori, thanks for staying up so late. You can go to sleep now. Thank you, everybody.
Thank you.
Thank you.
Bye-bye. Good night.
Bye.
Bye-bye. Have a nice